Hi everyone, I am Ziya, PhD student from Turkey at Fred University. Uh, we um, we had prepared with Professor Dr. Mehmet Karakose this article. Our article title is Proximal Policy-Based Deep Reinforcement Learning Approach for Swarm Robots. This article was created as follows: abstract introduction, theoretical information about deep reinforcement learning, simulated robot swarm application, and conclusion. In the study, it's aimed that three different robots in a limited area learn to move without hitting each other, fixed obstacles and boundaries of the field. These robots have been trained using the deep reinforcement learning approach and proximal policy optimization policy. Instead of using value-based methods with discrete action space, proximal policy optimization that can easily manipulate the continuous action field and successfully determine the action of the robots has been proposed. PPO policy achieves successful results in multi-agent problems, especially with the use of the Actor-Critic network. In addition, information is given about environment control and learning approach for swarm behavior. We propose parameter sharing and behavior-based method for this study. Finally, trained model is saved and tested in 9 different environments where the obstacles are located differently. Now, we can say about learning approach. There are three different learning approach in literature. One of these central learning and simulation learning, and the third one is parameter sharing. Central learning approach is an approach in which all robots in the environment are trained by a single model. The trained policy determines a joint action by evaluating the action experience from all robots. In simultaneous learning, each robot is responsible for learning its own policy. Therefore, each robot performs its own action. Thus, more than one policy can be trained at the same time. In parameter sharing, a single policy is trained by the swarm. However, each robot chooses its own action, thus the policy can be trained faster. In the study, we present behavior-based control as environment control and parameter sharing as learning approach. Now, we can say about the reinforcement learning that used in our study. In figure 1, a basic reinforcement learning architecture is shown. The main purpose of an agent in reinforcement learning is to learn how to maximize its target performance or minimize the cost of punishments by interacting through an environment. And in figure 2, a basic neural network architecture is shown, and in figure 3, the reinforcement learning network architecture is shown. Deep reinforcement learning is a method developed to solve the problems that arise in reinforcement learning. Since the performance of the Q table in limited environments cannot be shown in unlimited environments, artificial neural networks have been used. Generally, deep reinforcement learning constructs use a deep neural network to calculate a nonlinear value from perceptual inputs to action values or ability to move. About Actor-Critic, we use this structure in our network. Reinforcement learning agents predict, politicize, and value a function using value approach called actor and critic representation, respectively. The actor represents the policy that chooses the best action to take based on exciting observations. Critic represents the value functions that predicts the expected accumulated long-term reward for the current policy. Policy-based agents rely on the outcome of their actor-critic network to learn the most appropriate action. In this tutorial, agents use deep neural network-based action estimators for actor-critic. Both actor and critic have similar network structures. Proximal policy optimization is a model free on policy gradient-based reinforcement learning method. This method is a kind of policy gradient training ranging from sampling data through environments interaction and optimizing a piece of objective function using stochastic gradient. This can the objective function improves the stability of education by limiting the extent of policy change at each step. Agents using the proximal policy optimization algorithm can be trained in discrete or continuous environments of observation and action. In the training phase of the PPO agents, estimates the probabilities of occurrence for each action in the area where the action takes place and randomly selects the actions according to these probability values. Interacts with the environments using the current policy before using meaning batch to update actor critic parameters. Now, as shown in figure, there are three robots. This is our simulated area, training area. There are three robots represented by circles in the training environment. Robots are represented by red, blue, and green circles. Each robot paints the area it covers in its own color. The black colored squares represent the obstacle in the environment. This study focuses on three different agents cleaning at the same time and in same environment. The simulation environment demonstrates the competitive mission based on a collaborative and concurrent learning approach in which three different agents are trained to explore all areas. During the training phase, they will try to clean up places that have never been visited as much as possible. In the table, agents receive the following rewards and penalties at each training step: plus 1 point for scanning a previously undiscovered cell, minus 0.5 points for each illegal action, 0.05 points for each action that results in a move, minus 0.1 for each action that does not result in a movement, and plus 200 points for each robot during the episode if the training area is fully scanned. And table in the left table shows the action an agent can take during the training phase. We have five action. One of these zero weight, one up, two down, three left, and four right action. During the training phase, each episode consists of 500 steps. In total, 1,500 episode was trained, and agent's training is stopped when his average reward for 100 consecutive episodes is 80 or more. Table shows the parameter values used in training. We used hyperparameter for this training. Max episodes is 1,500. Max steps per episode 500. Score averaging window LED 100. Stop training value 80. We said this. And in this slide shown about results this training. Now we have four graph. Figure 1, figure 3, figure 2 is about agent, and last one, figure 4, about completion percentage of training environment. Now, after training, as shown in figure 1, the robot led by agent as a drum, a steady reward episode plot. During the training, the average reward is minus 46.21. After the first 500 steps, it's seen that the robot started to get to know the environment and how to get the most points from the episode consistently. Graph of agent B is shown figure 2. When the graph is examined, it is seen that it's constantly scanning the area after the 600th episode. Additionally, although there is a decrease in the average reward in the last 150 steps, it managed to compensate for this decrease. Towards the end of training, the average reward that robot B received during the training is recorded as minus 19.57. Figure 3 shows the training graph of agent C. When the graph examined, agent C shows a less stable trend than the other two agents, although it has achieved stability in the last 200 steps. It has not been successful in the previous episodes of the education. The average reward received by robot C during training minus 55.72. Figure 4 shows the graph of how much of available environment is completed by three robots. When the graph is examined, it's seen that the environment is completed approximately 10 times in the range of 80 and 100%. This number is directly related to step number parameter in each episode being 500. Increasing this parameter may increase the scanned area surface, but the total rewards robots receive will decrease. When the last when the last 100 steps are examined, it's noticed that the completion percentage approach to 80. The red line shown in figure 1, 2, and 3 indicates the average total reward the robot has received in each episode. Blue points indicate the rewards received in each episode.
Ziya, please just have in mind that you have only a couple of minutes left. So,
how much?
You should already finish maybe 2 or 3 minutes.
Okay.
Just
Okay.
keep up the pace.
About conclusion, last one in the study, the training problem of swarm robots in a limited area discussed. In the solution of the problem, deep reinforcement learning algorithm is trained using proximal policy optimization and actor-critic model. At the end of 1,500 episodes, it's concluded that three robots successfully learned the environment and tried to get maximum score. The use of CNN artificial neural network in both actor and critic network plays an important role in the success of training. When the episode reward graph all three robots is examined, it's seen that they have completed training proportionally and consistently. If one robot had received too many consecutive rewards, at least one of the other robots would fail to train. So it can be said that the education was successful. Finally, the results on the testing data verify the proximal policy optimization agents can adapt to different environment scenarios. That's all. Thanks for listening.